A kayaker 120 meters east and 350 meters north of his campsite is moving with the current at 2 meters per second to the south. He begins to paddle west, giving the kayak an acceleration of 0.2 meters per second squared for 15 seconds. So an important thing to realize in this problem is that the constant acceleration is not coming from the force of gravity. The constant acceleration is coming from the kayaker paddling. So our acceleration is going to be 0.2 meters per second squared, and he's paddling to the west. So the acceleration is 0.2 meters per second squared to the west. Okay, so this problem is going to be different than all the other problems that we've looked at because the acceleration is not due to gravity. The kayaker is 120 meters east and 350 meters north of his campsite. So let's do this. Let's say this is north, this is south, this is east, this is west, and we'll put the campsite over here somewhere. So 120 meters east and 350 meters north puts the kayaker somewhere over here. Okay, and then we can also say 120 meters east and 350 meters north. Moving with the current at 2 meters per second to the south. So the current's going this way at 2 meters per second before the kayaker begins to paddle. So at event 1, at the moment the kayaker begins to paddle, the kayaker is moving with the current, so the initial velocity, VI, is equal to 2 meters per second. Since I have not chosen a coordinate system yet to give the direction here, I'm just going to say 2 meters per second south. Okay, then he begins to paddle west, giving the kayak an acceleration of 0.2 meters per second squared for 15 seconds. Okay, so then let's just do this. Let's say delta t is equal to 15 seconds, and we can go from here. We do have to fill out the table completely in this problem. If we didn't have to fill out the table completely, we could actually solve the problem without choosing a coordinate system. But we are going to have to choose a coordinate system in order to fill out the table. Let's put the origin right at the campsite, which you do not have to do, but let's do that anyways. And say this is x, and this is y. Okay, now I can start filling in my table. And event 1 is at the moment the kayaker begins to paddle. So before the kayaker was just moving with the current. And event 2 is 15 seconds later. And I don't know 15 seconds later if the kayaker is going to continue to paddle or stop paddling, so we'll just call that 15 seconds later. So t1 is equal to 0, t2 is equal to 15 seconds. If I say the origin is at the campsite, which you don't have to do, you could say the origin is where the kayaker begins initially. If the origin is at the campsite and this is the x direction, we are initially 120 meters in the positive x direction and 350 meters in the positive y direction. Because your initial velocity is to the south, if we say that would be north, would be the positive y direction, this would be minus 2 meters per second, and there is no x component here, so that would be 0. But you are going to end with an x component for the final velocity because the kayaker is going to paddle to the west. Normally, we have v1x is equal to v2x because the acceleration is in the negative y direction due to gravity, but in this case the acceleration is in the negative x direction, so the y velocity is not going to change because there's no acceleration in the y direction. The acceleration is 0.2 meters per second squared west, so that's the negative x direction, so this is negative 0.2 meters per second squared. I don't know where the kayaker ends. I'm going to have to figure that out. I do know the acceleration in the y direction is 0, and by this equation here, since ay is equal to 0, v2y is equal to v1y, so I can say this is negative 2 meters per second. Okay, and then I can draw my vector diagram. We start where the kayaker started from, end where the kayaker ends for the position vector. I'm not actually sure exactly where the kayaker ends, so let's do it this way. Instead of drawing the position vector first, we'll look at the velocity. And I take the initial velocity, multiply it by delta t. I know the initial velocity is to the south. So this is v1 times delta t. And I know the magnitude of v1 times delta t, magnitude of v1, that is 2. So this is 2 meters per second. Delta t is 15. So this is 30 meters. Okay, so the magnitude of this is 30, but it's pointed in the negative y direction. The acceleration is to the west. So my acceleration is pointing this way. And for the acceleration vector, I have to multiply it by 1/2 and delta t squared. So this is 1/2 times the acceleration times delta t squared. 1/2 times the magnitude of the acceleration times delta t squared gives me 1/2. The magnitude of the acceleration is 0.2 meters per second squared. And then I multiply that by 15 seconds squared. And that gives me 22.5 meters. And then if I place the v1 delta t vector tip to tail with the 1/2 acceleration times delta t squared vector, I add those two vectors together, and the resultant vector delta r starts where the v1 starts and ends where the 1/2 acceleration times delta t squared vector ends. And this would be the y component of that vector, so this is delta ry, and this is delta rx. Well, the magnitude of this is equal to 30 meters, so that means the magnitude of delta ry is equal to 30 meters. And since the x component of the delta r vector is equal to 1/2 acceleration times delta t squared, the magnitude of this vector is equal to 22.5 meters. But this is pointed in the negative y direction, and this is pointed in the negative x direction. So I have delta ry is equal to negative 30 meters, and delta rx is equal to negative 22.5 meters. Now, if you had put the origin at the initial position for the kayaker, you would be done at this point. You just take these values and put them in the table. But because I did not do that, I have to say r2x is equal to r1x plus delta rx. r2y is equal to r1y plus delta ry, and that just comes from delta r12 is equal to r2 minus r1. So that's where we get that from. So r1x is equal to 120 meters. Then we subtract 22.5 meters from that, and we get 97.5 meters. So that goes in my table up here. This is 97.5 meters. You could round it to 98 if you want. And then for r2y, r1y is equal to 350 meters. Delta ry is equal to minus 30 meters. And that gives me 320 meters. That goes in here, 320 meters. What is useful about putting the origin at the location of the tent is that now in my table, this tells me where his final position is in relation to his campsite. So to get back to his campsite, he still has to go 97.5 meters to the west and 320 meters south. Okay, so actually we're not done at this point because we still have v2x. So instead of drawing a vector diagram, usually it's this equation that we would have to use to finish the problem, but in this case, because our constant acceleration is in the horizontal direction, we're going to use this equation to finish the problem. So I have v2x is equal to v1x plus ax times delta t. v1x was equal to 0. That makes things easy. So v2x is equal to 0. Acceleration is minus 0.2 meters per second squared times delta t, which is 15 seconds. And finally, that gives me -3 meters per second for my final velocity. I can put that in my table here. This is -3 meters per second, and I finished filling out the table, so that concludes the problem.